Okay, so we wanted to spend a few minutes walking through practice exam for practice exam 2. I'll note here that the real exam might not be quite this long, so I went a little long on the practice exam questions. Alright, Kirchhoff's rules. So Kirchhoff's rules are the ones, the junction rule and the loop rule. And for the junction rule, that says that the sum of the currents flowing into and out of any junction in a circuit add up to 0. So the current that is going into junction A is easily identified as the current that is traveling through the 3.9 ohm resistor, so we can assume that it's traveling in this direction because we have the positive terminal of the 12 volt battery here. So it's a good guess for the direction. If we guessed wrong, then when we solve the simultaneous equations, we come up with a negative number, and that would be fine. We can assume that the current coming out of or going through the 6.7 ohm resistor is positive going into junction A, so plus I 6.7 ohms, and then all of the current leaves junction A and would travel out through the 1.2 ohm resistor, so minus I 1.2 ohm, and the sum of these three, positive, positive, negative, all add up to a number that is 0. So there's 0 current kind of sitting there forever on junction A. Alright, so that would be a Kirchhoff rule question that I could ask on the exam. Or I might ask you to do a loop rule, right? A loop rule is to go all the way around a loop and do the voltage rises and drops. So I'd say, alright, so maybe I'd identify this loop here on the left, and I'd say, okay, so you're going to start at the top of the 12 volt mountain, so 12 volts minus I 3.9 ohm times 3.9 ohm. That's another way of saying voltage, right? The current times the resistance, V equals IR, minus I 1.2 ohm times the 1.2 ohm resistor, minus I 9.8 ohm times the 9.8 ohm resistor, would take us all the way back to the beginning. We'd have that loop on this side. We could also do a loop on this side, or we could do a loop around the whole outer edge. We have 3 loops that we'd have available here. I think we only have 2 unique junctions. So we'd have junction A or junction B. Whether we label junction B here or here wouldn't matter. It's the same current going into and out of that point. So that's the case. Alright, so number 2. The filament of a light bulb has a resistance of 50 ohms. A voltage of 120 volts is connected across the filament. How much current is in the filament? So it's Ohm's law. It's always going to be Ohm's law over and over again. So V equals IR. So I equals V over R. The voltage is 120 volts. The resistance is 50 ohms. That means the current in this filament is 2.4 amps. Always look to Ohm's law. Okay, so the resistance of a bagel toaster is 40 ohms. So to prepare a bagel, the toaster is operated for 1 minute from a 120 volt outlet. How much energy in joules, is delivered to the toaster? Alright, so to get to energy in joules, we're going to say, okay, so power has units of watts, which is joules per second. Energy then is joules. So watts, we can say power equals IV, and we could figure out the current for this arrangement if we wanted to, right, just using Ohm's law. Or we can say power equals V squared over R. We're given V, we're given R, so we could do that directly and have that answer. So power equals V squared over R, 120 squared divided by 40 gives us, it's a 360 watt toaster. And if we run that 360 watt, 360 joules per second toaster for 60 seconds, then that would be 21,600 joules of energy delivered to that toaster. Okay, I guess this one didn't work out too well, how I have it placed here. Can I move this? Hey, look at me. I'll move one of those pieces of paper down. Oh, but I left behind the plus and minus pieces. Oh, I had two different lines there. That's crazy. Can I find it? I think there's a negative sign here somewhere. Got it. Okay, so small bits of paper are attracted to an electrically charged comb. Explain this behavior. Well, this electrically charged comb, oh, I have to move all of the negative signs there, huh? I'm not going to move all of them because that's too much work for me right now. This negatively charged comb, we've given it negative charges, so it has extra electrons, so it has a net negative charge. And then I bring it close to small bits of paper. When I do that, the paper becomes polarized. The negative charges are repelled, leaving behind positive charges on one side of the paper. Now, because paper is light, the gravitational force is pretty small compared to the electrostatic force, and so the little bits of paper jump up and attach to the comb. Nominally, what would then happen is they would then pick up some of those negative charges, and then they would be repelled again. You don't often get to see the whole thing taking place there, but that's the idea there, that what happens is that the paper becomes polarized. If it's polarized, it's attracted, and we actually see it jump and attach to it because it's tiny and light. Alright, so make a qualitative sketch of the electric field lines produced by two charges, positive Q and negative Q, separated by distance d. So I guess I should have labeled my distance d here. But I have two charges. The electric field lines are going from one charge to the other charge. It's taking curves on the far sides. The arrowheads are terminating on the negative charges. The arrowheads are originating from the positive charge. And if I had, positive 2Q and negative 2Q, then if I drew that side by side, I would have twice as many electric field lines for the second one. There's no rule on how few you have to do with a single charge, but the rule is that if you double the charge, you have to double the number of electric field lines. Okay, so number 6, an automobile battery is being charged at a voltage of 12 volts and a current of 19 amps. How much power is being produced by the charger? Power equals current times voltage. Current times voltage, 228 watts. That was nice and easy. Okay, the current through the 5 ohm resistor will be. So just take a moment and appreciate that if you sat down to do this problem and you're looking for the current that is running through this 5 ohm resistor, I have no idea. In order to figure that out, first I have to figure out how much current comes out of the battery. Right, that's my first step. Then when I know how much current comes out of the battery, I'll figure out the voltage drop across the 4 ohm resistor, because all of that current will go through the 4 ohm resistor. And then I'll figure out the voltage drop across this bottom pathway, because it's going to be the same voltage drop for the rest of the circuit, because these two pathways are in parallel. Once I know the voltage drop across this pathway, then I can figure out how much current comes through this pathway, because I equals V over R, and I know the voltage and I know the resistance. So in order to do all of that, this is a pretty difficult problem. First thing I do is figure out the equivalent resistance of the circuit. So all of the current goes through the 4 ohm resistor, so that's in series with whatever comes after it. And then it splits off into two pathways that are parallel to each other. Each of these parallel pathways has two resistors that are in series, so that's where I'll start. I'll simplify there. The top series resistance here is just adding them together, so 3 ohms up top 6 ohms down at the bottom. Then I'll figure out the parallel resistance. 1 over R1, 1 over 3, plus 1 over 6, and then I invert that, and I get the parallel resistance for those two pathways to be 2 ohms. Alright, now the overall, the equivalent resistance of the whole circuit is going to be 4 ohms plus 2 ohms for 6 ohms. That tells me that the current that comes out of the battery, I equals V over R, is 3.33 amps. Now that I know that, I know that 3.33 amps all goes through the 4 ohm resistor, meaning that there's a 13.3 volt drop across this one resistor, and that means that I have another 6.7 volts before I get back to the battery. So I can jump ahead now and say, okay, through this bottom pathway that has a resistance, a total resistance of 6 ohms, I'm not just doing the 5 ohm resistor, I'm doing the whole pathway because the same current will go through the whole pathway. 6.7 volts divided by that 6 ohm pathway tells me that 1.11 amps goes through this bottom pathway, therefore 1.11 amps goes through that 5 ohm resistor. Alright, if I want to look at that same circuit, the current from the 20 volt battery will be, I figured that out already, 3.33 amps. So that's good. So one hard question, but then I got 2 answers out of it. So that was nice. Alright, number 9. I have 3 resistors. 25, 45, and 75 ohms, and they're all connected in series, and a 0.51 amp current passes through them. What is the equivalent resistance, and what is the potential difference across the 3 resistors? So the equivalent resistance for series, just add them together, 145 ohms, and then V equals IR, the current 0.51 amps times that 145 ohm equivalent resistance gives me 74 volts. Okay, this is a conceptual question. 2 charged spheres are attached and insulated from frictionless sliders on an air track. The charge on sphere 1 is negative, the charge on sphere 2 is positive. The magnitude of the charge on sphere 2 is 3 times the magnitude of the charge on sphere 1. Which of these diagrams will give us the answer? Alright, so one thing you can look at is the magnitude of the forces. The length of these arrows is the magnitude of the forces. And the force, the electrostatic force, equals KQ1 Q2 over R squared. It doesn't have a separate value for each sphere, for each object, each participant in that. The electrostatic force exists because both particles are there, and it's the same force acting between the two of them. Gravitational force that the Earth exerts on me is the same as the gravitational force that I exert on the Earth. They're the same. So first of all, we have a positive charge and a negative charge, so it's an attractive force. And then it is the same force, and so when we look at these options, these two are both repulsive. That can't be right. This one, we have a smaller arrow for the smaller charges and a bigger arrow for the bigger charges. That's not right. It's the same length of arrow for both, and it is attractive. Okay, Ohm's law states that V equals IR, or I equals V over R. Circuit contains a 5 ohm resistor and an adjustable power supply. The power supply can be set to supply any voltage between 0 and 10 volts. So complete the plot of current versus voltage. Indicate a scale on the vertical axis. So 5 ohm resistor. I don't know where I got confused there, but I decided to go with 10 ohm resistor. Yep, don't know why. Oh, here it says 10 ohm resistor. So I guess we're going with the 10 ohm resistor in the picture rather than the 5 ohm resistor in the question. So doesn't matter because we're just making a graph, but I equals V over R. So the current, when we set our power supply to 1 volt, 1 volt divided by 10 ohms gives us 0.1 amps. So I would say, okay, 1 volt, 0.1 amps. I would draw that in there. And then 2 volts, 0.2 amps. So 2 volts, 0.2 amps. And I keep plotting it, and I would get a straight line. Straight line for current divided by voltage. All right. This is a fun one. Wink, wink. You can't see me wink when it's just my voice. This is a question that I might ask on the exam because it's just a good rundown, and I can easily change the numbers, can't I? I can say you're given 3 200 ohm resistors or 3 50 ohm resistors. Whatever I want to do, I can just change the words in the question and have you show me that you know how to do both series, parallel, and then some complex circuits. So isn't that a good exercise? So hey, if I have one 300 ohm resistor, that has an equivalent resistance of 300 ohms. Not very tricky. 2 300 ohm resistors in series is 600 ohms. Again, pretty straightforward. If instead I set it up in parallel, skipping ahead, 1 over RP equals 1 over 300 ohms plus 1 over 300 ohms. The equivalent resistance there is 1 over that number, and that would be 150 ohms. Can do that as well for 3. Here, my top pathway is 2 300 ohm resistors in series, so that's 600 ohms up top, 300 ohms on the bottom, so 1 divided by 600 plus 1 divided by 300. Then I invert that answer. I get 200 ohms of equivalent resistance. Here I have one thing in series with this pathway in parallel, so 1 over 300 plus 1 over 300, I think we did this one already, is 150 ohms. 300 is 300 ohms, and those are in series with each other, so 300 ohms plus 150 ohm equivalent resistance gives us 450 ohms. I like that question. Hey, this is another one that's classic. You would see this on exam 2 any number of times. Maybe not your time, but maybe. Remember, when we do electrostatics, when we give charge to an object, we do that by either removing electrons to give it removing electrons to leave behind a net positive charge, or adding extra electrons to give it a negative charge. So, if you have an electrically neutral object and you give it a positive charge, what we've done is removed electrons, and electrons do have some finite mass, so the mass of this object decreases. To give it a positive charge, we didn't add protons and have the mass increase. That's not right. We removed electrons and the mass decreased. If we give something a negative charge, then we're doing that by way of adding extra electrons. Therefore, it would have a net increase in mass. Really tiny increase, but some amount. All right, if you've stored 2 times 10 to the negative 6 coulombs of charge at a potential of 3 volts, you have yourself a capacitor. The capacitance of this capacitor, look at the equation sheet, Q equals CV. So C, the capacitance, equals Q over V. Q, 2 times 10 to the negative 6 coulombs, divided by V, 3 volts, gives me a really tiny number, 6.67 times 10 to the negative 7th farads. Okay, we have 2 small spheres, initially neutral and separated in distance by 2.2 meters. If I take 150 electrons from one, initially neutral, if I take 150 electrons away, I've left behind a positive charge, and place those 150 on the other one, I've given that a negative charge. Then, first of all, what is the magnitude of the electrostatic force that acts on each sphere? It's going to be the same force acting on both. And is it attractive or repulsive? Well, I can answer part B right away, because if I took something neutral and then I took some electrons away and dumped it on the other one as positive, one as negative, that's an attractive force. 150 electrons has a charge of 150 times the charge per electron, 1.6 times 10 to the negative 19th coulombs. So a net charge on each particle of 2.4 times 10 to the negative 17th coulombs. So one sphere has positive 2.4 times 10 to the negative 17th. The other one has negative. So force equals K Q1 Q2 over R squared. K Q1 Q2 divided by 0.2 meters squared. We get 1.3 times 10 to the negative 22nd newtons. It's not much force, but it is some amount of force. Hey, an ion with a charge of positive 3.2 microcoulombs, that's positive 3.2 times 10 to the negative 6 coulombs, is moving at a velocity of 100 meters per second. The ion enters a region where the magnetic field is 2 Tesla, and this field is directed perpendicularly, perpendicular 90 degrees, so that means sine of 90 degrees is 1. The magnitude of the force upon the ion from this interaction in this field will be force equals QVB sine theta. Q we just have to make sure we convert to coulombs and don't keep it in microcoulombs. V velocity, B sine theta, 6.4 times 10 to the negative 4th newtons. Hey, we have the same question as before, similar question about capacitance. Sometimes I ask the same question over and over again, can't help myself. Alright, so looks like I asked that one before, so there you go, another capacitance question. Hey, number 18, a 1.5 volt battery is connected to 3 10 ohm resistors arranged in parallel. So I can figure out the equivalent resistance there without too much challenge. A 0.15 meter segment of the wire lies between a 5 Tesla permanent magnet as depicted below. That looks perpendicular, so sine of 90 degrees. What is the force on the wire? Force equals IL, it's a cursive L, length of the wire that is between the magnet in the magnetic field, B sine theta. The current equals V over the equivalent resistance. The equivalent resistance is 1 over Rp equals 1 over 10 plus 1 over 10 plus 1 over 10. So 1 over that is 3.33 ohms. The current then is 1.5 volts divided by 3.33 ohms, 0.45 amps. So the force equals I, 0.45 amps, L, the length inside there, 0.15 meters, B, 5 Tesla, sine theta, so force equals 0.338 newtons. Gave us the direction of the force, so we didn't use our right hand rule that time. You create an electromagnet by wrapping wire around a piece of metal. Draw the magnetic field lines for your magnet. I guess I didn't do that. Which letter represents north magnetic pole? So if I was going to draw my magnetic field lines, I would draw arrows. Maybe I could do that. I don't feel like doing it. Insert, drawing, shapes. How do you do the squiggly lines with the arrowheads? Is it this? Oh, come on, don't stop. Oh, I didn't do that very well. Insert, shapes. I want lots of little places that I click. Why is my functionality limited? Oh, maybe I wanted this one. Oh, but that's what I just did. Oh, guys, I stink at this. I'm so sorry. Forget it. Pretend that I'm just drawing lines that go from one place to the other. So start Alright, so first of all, before I do bad arrows that aren't working, let's first say that that we'd figure out where the north magnetic pole is. We have the positive terminal of our battery, and the current's going to wrap around like this, this. So I'm going to take my right hand, I'm going to curve my fingers in the direction that the current is traveling from back to front. If I curve my right hand fingers that way, my thumb is pointing this way to the letter C. That is the north magnetic pole. And then my arrows would go woo from C to A, from C to A. Start on C, end on A, north pole to south pole, and I draw a few magnetic field lines around that. Okay, two charged particles move at right angles to a magnetic field and deflect in opposite directions. Can one conclude that the particles have opposite charges? So it sounds intuitive that you could conclude that, but if the two charged particles enter the magnetic field in the same direction, then opposite charges is a valid assumption. However, they could come from opposite directions, in which case it only makes sense that they're deflected in opposite directions. So you can't be sure. Number 21. What is the acceleration of a proton moving with a speed of 9.5 meters per second at right angles to a magnetic field of 1.2 Tesla? So force equals mass times acceleration. Acceleration equals force over mass. So we can figure out the force like we've done before. Force equals QVB sine theta. Q is the quantity of charge on a proton. VB sine theta. We come up with a really tiny number for the force. And then the acceleration is force divided by mass, really tiny number, divided by a really tiny number. The mass of a proton I would have to give you on the data sheet equals 1.1 times 10 to the 9th meters per second squared. All right, transformers. Didn't mention this in lecture. You'd have to look it up in the chapter. I'll try to remember maybe to not put this one on the exam, although I like transformers. It's good stuff. The equation for transformers is that the ratio of the primary voltage to the secondary voltage is the same as the number of turns in the primary coil to the number of turns in the secondary coil. So I have this is how a transformer works. Outside your house and the power lines, the power is being delivered at a higher voltage, and then there's a step down transformer to bring 120 volts into your house. So we have the high voltage part of it, then the low voltage part of it, and so the primary voltage, is that what we're looking for? What is the secondary voltage? The secondary voltage equals VPNS divided by NP. So we count up the number of loops on each side. Primary voltage 110,000 volts times 4 divided by 12, the number of loops on the high voltage side, and we'd step down to 36,667 volts. Did I really just ask this question twice? Man. So the exam really won't be this long. Hey, draw the imaginary magnet formed within the coils as a permanent barb magnet approaches as shown. So this permanent barb magnet has a little rocket ship on the back of it. These are the magnetic field lines that I would have drawn before if I had done that. It's going toward this loop of wires. Just because we have a moving magnetic field, an invisible barb magnet is created by flowing electricity, flowing electrons through this loop of wire, and it's being belligerent. If the north pole is attracting, then this creates a north magnetic pole that opposes that motion. If it does that, then current would be flowing through the wire in such a way as to give it a measurable voltage. All right. The magnetic field of the Earth can be described as though there were a giant barb magnet in the center of the Earth. If we drew that, we would remember that the compass that I'm holding in my hand is a magnet with the north pole of my compass being attracted to what we call geographic North Pole, which must then be a magnetic South Pole. So it's off by a few degrees from the actual North Pole, but my bar magnet would look something like this with the magnetic field lines. And then we would see aurora borealis, other effects of charged particles being trapped in the magnetic field lines because they're concentrated at the poles. We don't notice it up in the sky above us so much because we don't have concentrated magnetic field lines. And hey, that finally takes us to the end of this exam. Only a couple of repeat questions. You can look for an exam 2 that is approximately the same length as exam 1, which was 16 questions, so that seems like a reasonable assumption how long exam 2 would be. Okie doke, see you!